The Spaghetti Bridge project, undertaken for Structures 1, is undertaken with an aim of choosing a bridge type and designing it by applying force physics that we have learnt throughout the semester. The bridge will then be built to our selected design, where it will be then tested to failure, where we will find its maximum strength resistance. The type of bridge design for a spaghetti bridge is crucial, as many bridge types are not compatible to be made out of spaghetti. To narrow down the selection of a bridge, we had to look at bridges that would be compatible with spaghetti to the specifications without going over the weight limit. For an example, we would not be able to build a suspension bridge with just spaghetti, as we would not have any material to act as a cable, and we thought it would be too weak over this length. A box girder bridge would be achievable. However, to build a box girder bridge over a span of 350mm, the weight would possibly be heavier than a restriction of 200 grams. A beam bridge was not chosen on the basis that it is reliant on the tensile strength of the spaghetti. As spaghetti is a brittle material that is weak in tension, this was not chosen. To combat these limitations, a truss bridge was chosen. This is because a truss bridge has elements of a suspension bridge with struts that hold tension and a top chord that shares the load with the bottom chord through the struts. To start the design of our build, we had to look at the restrictions that were in place for this build. The restrictions are: the bridge must have a clear span of 350mm, the maximum width of the bridge shall be 80mm, the bridge may not be heavier than 200 grams. The build started from a simple design of a truss bridge, composing of only diagonal truss webs. This was our starting point. Construction of the bridge was then undertaken, and the dimensions were 400mm long, 160mm high and 60mm wide. Each piece of the bridge was comprised of 11 spaghetti strands and were glued together. The pieces were held together while drying by using tape on either end. This method seemed to work as it kept the pieces from moving and allowed us to focus on building the bridge instead of holding the pieces together. When the pieces of the bridge dried, we began to build the bridge. Both trusses were built at the same time. However, we found a common problem. The pieces were difficult to assemble and had to be held in place until the bond was strong enough to hold itself together. Once the bridge was finally together, we realised that the bond between pieces was very weak and would not be able to hold much strain. We also started to understand more about compression and tension, meaning our diagonal struts would be considerably weak compared to upright struts with diagonal struts. This is due to spaghetti being weaker in tension compared to compression. The first bridge was too weak to hold even small amounts of weight, and the bridge broke before making it to the test apparatus. To combat these faults found, we made adjustments to our design. We used 3 upright columns and 2 diagonal columns. This is so the upright columns can take majority of the load. Only 2 diagonals were used per truss in fear of breaching the weight limit. To eliminate weak joins as a fault, we came up with a new cross-hatch style. This dried stronger and was easier to work with. Rubber bands were also used instead of tape during the build to make it easier to build, and building was quicker and there was no fear of breaking the spaghetti when taking the tape off. The final product was very neat and looked very strong. However, in another fear of being over the weight limit, the diagonal struts were removed. One flaw we found in the bridge was where the load-bearing plate for the test should be sitting central. However, we had a central strut in the way, and what we should have done was put 2 struts either side of the plate, so the load bearing was in the middle instead of on one side. The bridge's final weight was 153 grams, meaning we were under the weight limit by a decent margin, which was surprising to both of us. The test results for the bridge were pleasing, seeing as the bridge was not compact and did not have many load-bearing struts, and also being 50 grams under the weight limit. The final load of the bridge could hold 7 kilograms, which both of us were very pleased with the outcome. This outcome could not have been achieved without the changes we made from the first bridge. The improved joints helped majorly to hold the load. This is because we were using 2 or 3 points of contact on one joint instead of using just the single one. Being 50 grams under the weight limit indicated to us that we could have used additional struts within the trusses to add strength to the bridge. Only using 3/4 of the weight put us at a disadvantage compared to the rest of the class in regards to strength. But it is also a complement to a sound build of a bridge that had a good weight to strength ratio. Also, more attention should have been paid to where the testing plate sat regards to our struts. This could have added more strength instead of the 7 kilograms if the weight was central. Thank you for watching our video.